Does a car have enough velocity to go from the ground into space? Does a train? Of course not. They're too slow. Does a rocket? Yeah, that's what it's built for. So what is this minimum speed you need to grow from the Earth's surface into space? The answer is 11.2 kilometers per second. And we're going to show you why. Let's start with a diagram. So we have a planet right here. Here is its center of mass. So all its mass is concentrated there. Let's put a rocket on the surface of the planet. Let's call the distance between these two things r. So it looks like the radius of the planet, and it is. So let's assume that we launched the rocket. So now it's going to have kinetic energy. And we calculate kinetic energy by this formula. So m subscript 2 is the mass of the rocket, v is the speed of the rocket. And as it's going up, the Earth is it's attracting this rocket, and the attraction is called gravitational force, and it's given by F equals G times M1 times M2 over R squared. So we explained what R was. G is the universal constant that determines the strength of gravity between two objects. M1 is the mass of the planet, M2 is the mass of the rocket. So one thing here is that gravitational force is a force and kinetic energy is energy. So how do we relate these two things in order to get the minimum velocity? Because force is measured in newtons, it's a vector quantity. Energy is a scalar quantity and it's measured in joules. Vector means it has magnitude and direction. Scalar just means it just has magnitude. Okay, so we want to convert this force into like something similar to energy, at least similar to energy. Something that's similar to energy is something called work. Work is defined as force applied over distance. So we move something over distance using a force. So it's not exactly energy. It's measured in joules, the same as energy, but it's not. Why? So energy is defined as the capacity to do work. So it's the theoretical amount that we could do. Whereas work is the actual amount of energy transferred. Okay, so we're going to try to find the amount of work gravity does, or the negative work it does on the rocket, so that we can relate these two things. So let's start with a graph. So here on the y-axis, it's going to be the force. The x-axis is called the distance r. So the basic formula of work is W equals Fr. So the more the force you apply, the more work you do. The greater the distance you apply this force over, the more work you do. For the moment, let's assume that force is constant, so it's going to be a horizontal line. Notice that work is like the area under this graph. F times R is like the area under this graph. That's important. So we can think work as the area under a force distance graph. But we don't know whether, gravitational force is a constant force. It could have a graph like that. We don't know. But the key idea is that it's the area under the graph. So now we're going to have to put in some calculus. So for those who do not know calculus, this might be a little confusing, but I will in the next video prove this to you, why it works. But for the moment, just think of it as the area under the graph. So here we have integration, okay? And we have a negative sign in front of it because it's doing negative work. We have R2, R1, and we have f r dr. So r is the distance. This is a function of the distance. Why? Because the mass of the two objects are constant. The universal gravitational constant is constant. Only r is changing. You put negative g minus 1 minus 2 over r squared, which equals gm1 times m2. That is negative r. So yeah, we will prove this in later videos, but essentially what I'm just doing is I'm calculating the area under the graph. Right, here's where another key idea comes in. And this is also why we put this negative sign. So we're talking about conservation of energy right now. Initially, we had no energy, no kinetic energy, so we weren't moving the rocket, and it didn't have any gravitational potential energy. So, gravitational potential energy is the energy an object gains in a gravitational field when you lift it up. And so it had none of that as well because it was on the surface. So as it launched, that kinetic energy is suddenly, it's getting transferred into gravitational potential energy. Now, you can lose gravitational potential energy if you leave the gravitational field. And so once you barely escape the planet, you're essentially barely escaping its gravitational field. Therefore, you will have no gravitational potential energy. So in the end, you have zero energy, and you have at the start you had zero energy, and in the end you have zero energy. So how do we make this mathematically accurate? Well, we have to set r subscript 2 to infinity, because we want to make sure that gravitational potential energy is negligible. All right, so here is another important idea. Notice, so the work done so far is this thing, okay? So we set that into infinity, and then it turns out that it is 1 over r1. We evaluate it like this. We'll show you in a future video. So the work done, well, this is the gravitational potential energy. So now I'll show you. So when an object is going up, it's gaining gravitational potential energy, but the Earth is doing negative work on you. So when gravitational potential energy is positive, the work done by gravity is negative. When you're falling down, the change in gravitational potential energy is negative. But the Earth is doing positive work on you. So they're always the opposite of each other. So that's why we also put this negative sign. So they're the same quantity, just opposites. That's why we put that negative sign. So closing up, this was the statement that we made. The initial kinetic energy plus the initial gravitational potential energy must equal the final kinetic energy plus the final gravitational potential energy. Plugging this in, we should arrive to this, which must equal 0 plus 0. And so if we set these two things equal to each other by algebra, we just transpose it so they equal to each other. So we can multiply both sides by 2 over m, subscript 2 to get rid of the m on that side, to get rid of that. We find out that v, Once you square root it, it's going to be GM1R times 2. So we proved the formula, and now go check out my short and plug in those values. If you want to see more videos like this, please comment. So yeah, I will give that calculus some justification. Obviously, don't just believe it without seeing the proof. So we'll prove that